Materials engineering is about designing, processing, testing, and discovering materials, mainly solids. It's about analyzing the structure, properties, performance, and processing of materials and objects. In fact, if you do a Google search for materials engineering right now, you'll see this come up. And this basically says that all four of these things are connected, and by changing one, like the structure of a material, you change everything else. But let's first start with careers, like what would a materials engineer be doing or be needed for? Well, like I said in our aerospace video, aircrafts traveling at supersonic speeds are subject to so much friction from the air molecules that the aircraft can be heated to several hundred degrees Fahrenheit. The materials engineer might have to figure out or design the best material to use that can handle these conditions. Materials engineers are very important when it comes to cars. Did you know cars are designed to crumple when they are in a crash? They are made to have that accordion-like response, and it saves lives. The cars crumple to absorb energy from the crash, and they need the right material and structure to do this. If the car was extremely tough and no damage was done in a crash, all that energy would be transferred to the driver. The frame of the car may have harder metals at the top compared to the bottom because of how that will transfer energy from a crash away from a driver. How a car will be impacted in a crash is kind of predictable because that's how engineers design them, and a huge part of this is picking the right materials with the right properties. And on that topic, materials engineers deal a lot with fracture and how components fail. So you could work in a failure analysis lab where you have broken parts that can range from jet engines to computer parts and have to figure out what went wrong, and it's really about looking at the structure and material itself. The materials engineer who wrote this video with me had a job in a failure analysis lab where he had to look at the landing gear of a plane. But not shown here, the landing gear had a huge crack around it which almost broke it during landing. So he had to use a microscope and analyze the microstructure of the landing gear. This is a micrometer scale picture but tells us a lot. At this scale you can actually see where the crack originated from and how it physically propagated through the structure. The crack isn't shown here, but you'll learn how to analyze these in school. And guess what? Just like with the car, landing gear is designed to fail like this. The material and structure is designed so that if it failed, it wouldn't just snap. It would crack along a certain path so that during landing, even though there was a crack, the plane could still make it through the runway. So a materials engineer could also design how a structure will fail if and when it does. Then based on the failure analysis results, we can design even better landing gear and various other structures. Or maybe if a computer part failed, you're not going to do circuit analysis like an electrical engineer would, but you may be looking for a soldering issue where there's a connection problem and a component came loose from the circuit board. So again, you'd have to analyze this on a micro scale using a microscope and determine what happened and why. They also have to deal with corrosion, which is a big field for materials engineers, and you can even take elective classes on this in college. Corrosion is destructive to metal, so any pipes that carry some fluid will be subject to corrosion and need to be designed properly. Whether it's pipes that carry water to and from our houses, ones for oil, ones in our cars, and so on. Or various marine technologies like submarines need to be designed not to corrode from all the interaction with salt water. Planes also need to account for this, and there's many more. And different environments these are subject to, like freshwater, saltwater, oil, etc., cause for different types of considerations when designing them. Materials engineers need to take preventive measures to pick the right material to account for all this. You could work on biomaterials, which is something biomedical engineers take classes on as well. But biomaterials are used for constructing artificial organs or to replace bone or tissue, and these materials need to interact well with the human body and not cause harm. For example, there are hydrogels that are needed to repair damaged heart tissues. This incorporates biology and is something you could take an elective class on as well, or you could see in grad school if it interests you. You could work on making superconductors, which are materials that have no resistance to electron flow, like no heat or other form of energy is given off, unlike your electronics which get hot as you use them. And superconductors can be used for high-speed digital circuits, particle detectors, trains that use magnetic levitation and don't make contact with the ground, and so on. They can also work on materials processing and manufacturing. Materials engineering isn't just about analyzing properties of materials and how to use them, but also better ways to manufacture these materials, like with the fabrication of semiconductors that are used in our electronics. Electrical engineers may do circuit analysis with these, but how those components are made is done by other types of engineers, including materials. Or you could work on the study of carefully rearranging atoms and molecules to form new structures that have better mechanical, electrical, and magnetic properties for a material. This is also known as nanotechnology. The way the atoms are arranged are what gives the materials a lot of their properties. It's why some things break when we drop them, and why other things stretch when we pull on them. If we can manipulate the arrangement of atoms, then we can change the object's properties and how it behaves. We can use this to create solar panels that can absorb energy much better, all the way to making glasses that won't break when being dropped, but there are so many more applications. Materials engineers could make clothes that don't smell bad after use, tires that grip the road better, stronger tennis rackets, and the list goes on. But now let's see what you can expect in college and kind of zoom in a little more on these materials. So you're going to cover the 4 main classes of materials, which are metals, ceramics, polymers or plastics, and composites. And although you learn a lot about everything, there's a big focus on metals. Now when it comes to all these materials, big things we care about that you'll learn are the mechanical properties, electrical properties, thermal properties, as well as the atomic structures. Mechanical properties include hardness, ductility or an object's ability to deform when being pulled, brittleness, where a material is brittle if you pull on it and it breaks without much deformation. So if you have a material and you pull it, eventually it will break. If it's brittle, it will just snap. Glass would be an example of this. But if the material is ductile, it will actually be elongated and deformed before totally snapping, and certain types of steel would be an example of this. In school, you're going to learn how to analyze certain graphs which have stress or force over area versus deformation or strain, like how far it's been stretched. Then they'll give you some curve and you have to understand it. This shows that if you pull an object very hard, it only stretches a little. So you know this is a stiff material versus a more flexible one which might look like this, like for a rubber band. And there'd be more to these curves you'd have to understand, like its fracture point, ultimate strength, what the slope of that initial line means, and so on, that can tell you more things like how brittle it is and so on. And every material will have a different stress-strain curve. Nothing you have to worry about now, but realize this is something that you'd learn. And there's more mechanical properties, but you get the idea. Then you'll learn electrical properties like how well materials conduct electricity. Thermal properties would of course be how well heat can flow throughout an object. You'll learn the atomic structures and bonding within these materials, which is very important because sometimes those structures allow us to determine a material's properties. For example, take graphite versus diamond. Graphite is relatively soft while diamond is extremely hard, yet both are made out of carbon. This difference in mechanical properties comes from the way the atoms are arranged in these materials. And there's more properties like magnetic properties and optical properties, but this is the general idea. So now, like I said, you go over the 4 main classes of materials, and everything you just saw you will apply to all of these. But a big one you go over is metal. The main metals you go into include aluminum, steel, stainless steel, titanium, copper, and so on. One important topic dealing with metals you'll learn is heat treating, which I'm going to explain a little so you can see its applications. You're going to learn how to analyze a graph that has temperature versus time. The temperature may go up to something like 800 degrees Celsius and down to, let's say, 100. And let's say this is for something like steel, which would be solid at all of these temperatures, because again, you don't really go into liquids or gases. And the time may go from 1 second to something like 100,000 seconds, or about 28 hours. Then on the graph, you'd be given something like this. Don't even worry about what these are right now, just realize these are the different transformations the material can go through. Different materials have different looking graphs, just like this red and green curve actually represent 2 different steels. So let's say we heat up steel to about 800 degrees Celsius and start there. Then we cool it to 100 degrees Celsius in 1 second, so very quickly. That curve, or line in this case, tells us which transformations this material goes through during cooling. See how it goes through those regions with an M? This goes through different transformations than if we slowly cooled it to the same temperature over the course of about a day. So what does this do? Well, if it's cooled very quickly like that first line, that might yield a very hard but brittle material. If you cool the material slower, it may yield a slightly softer material, but that is much tougher and doesn't break easily. It's all the same material, but we can achieve different mechanical properties just by cooling it differently. Now moving on, you may do projects or reports on basic objects, but go into depth on the material beyond what you may know. These projects can be for anything, but since we are on the topic of metals, at one school students did a project on an ice cream scooper. Seems simple, but what you may not know is that there is heat conducting fluid within the scooper. This is designed to transfer the heat from your hand to the metal of the scooper, and this warms the metal so that when you scoop the ice cream, it kind of melts the ice cream, making it a little easier for you to scoop, as well as making it so that the ice cream does not stick to the metal. Also, you can't read the words on the box in this image, but on it says new aluminum alloy that helps resist corrosion. So hopefully you're seeing how the materials used in nearly everything down to a simple ice cream scooper are optimized by the designers, and how corrosion is a huge field as well. Now I want to skip to composites. This is something you may take an entire class on in undergrad. Composites are made up of at least 2 different materials from the other 3 categories. These are crucial because many technologies of today require materials with certain properties that cannot be met with normal metals, ceramics, and polymers. For example, when it comes to aircrafts, we are trying to find materials that are strong, stiff, and have low densities and more, which is a tough combination of properties to achieve. Often strong materials are also dense, as an example. So engineers are trying to design and find materials that can provide the properties we want to achieve, which is where composites can come in. So you're going to learn about these mechanical properties, look at stress-strain curves of fiber-reinforced composites as a random example, methods of manufacturing composites, and so on. Now I'm really not going to cover ceramics and polymers in any detail, but if you want to know some basic examples, ceramics might be like a china cup, a brick, or a dining glass. And polymers or plastics might include a bicycle helmet, pool balls, dice, and so on. Now these are very basic examples, but in school you cover more advanced materials that have engineering applications, like silicon carbide that can be used to create very hard ceramics, which can be used for car brakes all the way to bulletproof vests. Also note that there are many materials that we've all heard of, but there are way more that you probably haven't heard of. These are just a few out of hundreds that were just in an intro textbook on materials engineering. No, you don't have to memorize all of these, but this is a challenge with materials engineering because of the sheer amount of materials out there that all have their different properties. Now just briefly, when it comes to labs, the equipment you can expect to see would be like microscopes, tensile testers, hardness testers, and things like that. A lab you might do is cool a material very rapidly, then do tensile testing on it. You'll use a machine that pulls the object in opposite directions, which is what tensile stress is, and you'll notice the material is very brittle like we saw earlier. You'll use microscopes to look at the microstructures of various materials, which is very important. Like I said, you'll learn what these mean and how much they can tell you about a material. I said that they can reveal material properties, but they can even reveal how the object was made, like with heat treating and how fast it was cooled. For those wondering how much math you see during college, there is math and calculus, but it's not the majority of the curriculum. For example, in a kinetics class, which you will take, one thing you'll learn is diffusion and how atoms move throughout a material. So you may have a high concentration of, let's say, carbon. So to represent how the concentration changes over time, you would have to use calculus because the rate that concentration is changing at is not constant. Or remember that stress-strain curve? Well, the area under it is the energy absorbed, and for those who've taken calculus, you know this involves an integral. So you see there is calculus and definitely math like algebra and linear algebra that I didn't mention, but it's definitely not as much calc and higher level math as an electrical, mechanical, or aerospace engineer might see. Then as you can see, there's also a lot of chemistry which you will learn within your materials engineering classes. So if you struggle with math, you should expect it in this major and be ready for it, but you should also be able to handle it. Overall, materials engineering covers a wide range of sectors, and there are still many challenges that we face, and materials engineers are doing research to overcome these challenges. Whether it be to reduce the weight of cars and aircrafts, reduce environmental pollutants in the production and fabrication of various materials, or finding better materials for fuel cells to improve their efficiency. Aerospace, mechanical, and civil engineers are just a few examples of majors that also learn about materials and material properties in their curriculum, but as you can see, materials engineers dive much deeper. And lastly, while there is a distinction that can be made between materials science and materials engineering and how we categorize and define them, at least in terms of undergrad, at many schools it will just be called one or the other, and you will likely be in the College of Engineering if you go into this major. If you like this video, don't forget to comment, like, and subscribe, and I'll see you all next time.